Alright, so this video is going to focus on energy changes as they apply to both state changes and within warming a state. So just to review some terms that you did in your first chemistry class, the heat of fusion is just referred to as delta H of fusion, and it's telling us how much energy would need to be transferred per gram of substance to change a solid to a liquid at its melting point. You could also use it to go from a liquid to a solid. It would be the delta H of crystallization or freezing. Heat of vaporization works very similar to heat of fusion. With the amount of energy it takes to turn a liquid into a gas per gram at its boiling point. You could also look at both of those in terms of kilojoules per moles or joules per moles, as long as it's an energy unit per an amount. When we are dealing with phase changes, the calculation we use is a little bit different than a temperature change because the temperature remains constant. All that's changing is potential energy, so we actually use Q equals M times delta H. And depending on what changes you're going through, as you transition from one state to another, you would have to calculate the energy associated with being within that state, as well as any phase changes that are associated. So if you're going from like solid to a liquid, you would have the energy associated with being a solid, then the energy of the phase change from solid to liquid, and then the energy warming the liquid up. And you could do the same thing between a liquid and a gas, or if you were going between all three states, you would have to account for two phase changes. So this is just a graph kind of showing you what happens with water as heat is applied. We see that ice, if it starts out below zero, will transition to water at 0 degrees Celsius, its freezing point, and then, its melting point, and then it will transition from liquid to gas at 100 degrees Celsius, water's boiling point at 1 atmosphere. So the first question, I think the only question we're going to look at tonight, is how much energy does it take to convert 25 grams of ice starting at negative 25 degrees Celsius to steam at 115 degrees Celsius. We can use a graph like this to basically represent phase changes. You've seen this before, as well as temperature changes. When we see the flat lines on the graph, that's where a phase change is occurring. So specifically for water, we would see the melting point as well as the boiling point of water. The sloped lines represent the state that you're in, solid, liquid, and gas. And then the phase changes are, as we talked about previously. When you are dealing with water and you are just warming a substance up, you have a sloped line because you're undergoing a temperature change. We use mCp delta T to calculate the energy change associated with it. And those are the three CP values that are associated with the different states of water. Again, it could be joules per gram degrees Celsius. It doesn't matter whether it's Kelvin or Celsius. Because we're talking about water specifically, water melts, ice melts at 0 degrees Celsius, water freezes at 0 degrees, and water boils at 100 degrees. So the energy associated with that change would be M delta H. And the delta H values for that phase change are listed below as well. So in our example, we are going to go through all three states. We're going to go from ice to steam. And so if we were going to build a graph just specifically for our question, you would have on there the three states for the slope lines, your phase changes, the temperatures associated with those phase changes, and then we're also going to include an initial temperature, which was negative 25 degrees Celsius, and a final temperature. What that's showing me is that I will need to do a calculation for the first slope line, the next flat line, the second slope line, the second flat line, and then I'll go partially up the third slope line. So I will have 5 different calculations to do, depending on what state I'm in and what temperature changes I'm undergoing in that state. So the first one is warming the ice up. We have 25 grams, so that M is going to stay constant, but because we are ice, our CP is 2.06, and we're going through a temperature change of 25 degrees Celsius, so that's 25 Kelvin. We would next go through the phase change for solid to liquid, that at 0 degrees Celsius, so we use M delta H, the delta H for the phase change from solid to liquid, and our mass 25 grams. The third line is a sloped line, and this time we are a liquid. So what changes is our CP value. We go for the liquid form of water, 4.184, and we go through the temperature change that is occurring from the end of that line to the beginning of the line, so between 100 and 0. So the temperature change would be 100 degrees. We now have hit another flat line, and we are changing from liquid to gas. So we want to find the delta H value associated with that particular phase change, 2260, and multiply it by its mass. And then finally, in our last part, we want to warm the water that has been changed over to vapor at 100 degrees to superheated steam at 115 degrees Celsius. So we use a CP associated with that that temperature change, 1.86 joules per gram Kelvin, and multiply it by the difference between the two temperatures, 115 and 100. And so we get a difference of 15 Kelvin. Again, the temperature changes that you're seeing here are associated only with the part of the graph that they're applicable to. So you will never have a temperature change for water that goes all the way from 115 to negative 25. You will always have to, whenever you transition from a sloped line to a flat line, when you transition between one phase to another, you will have to transition to a different equation to account for the change of energy that's taking place. Slope lines are where we have kinetic energy changes. Flat lines are where we have phase change, potential energy changes. So when we cancel out our units and multiply across, account for our sig figs, I got 1300 for the first multiplication, 8300 for the second one, 10,000 for the third one. It would be a line over the first zero for the two sig figs, 57,000 for the fourth one, and 700, again a line over the first zero to represent the two sig figs. I did those separately because multiplication is a higher order of operations than addition. At this point I can add them together, and what that tells me is that it requires 77 kilojoules or 77,300 joules of energy to warm ice at 25 grams of it all the way up to steam, going between those two temperatures. And that should be enough to get you through the last couple of questions for the review.